All right, so let's go back to moment maps and symplectic geometry. And last time I promised you that this was all we needed for the background on group actions, but now I realized I need a little bit more. So we still continue probably for 1 hour this background on group actions, and then we go to Hamiltonian G spaces. So, well, it's a little bit a pity this desk no longer exists. Well, okay. So more on group actions. Well, we have a group acting on a manifold, and we know that this action induces a map from the Lie algebra, which is just the tangent space to the group at the group unit. Into the space of vector fields on M. So the notation is as follows. So we have an element of this vector space, and it is mapped to a vector field which is called the fundamental vector field. So in fact, what we can introduce is the following set. Let me call it this kind of calligraphic Z letter. So Z of Xi. So this will be the set of points of M where the corresponding fundamental vector field vanishes. So that's the set of zeros of Xi M. So we'll come back to this set very soon, but let me introduce or recall one more notion. So let me denote by G Xi the one parameter subgroup of G which is spanned or which is generated by the Lie algebra element. So maybe in our standard example, if G is a k-dimensional torus, then the Lie algebra is R to the k, and if I choose here a vector, Xi1, Xik, it is mapped by the map exponential of T Xi with T some real number to T Xi1, T Xi2, and so on, T Xik, and this is all modulo 2 pi. So that's an element of Tk. Maybe just a very simple, very simple thing to remind you. So if we choose k equal to 2, and to think of a torus as a square with the sides identified, so then as you probably know, the possible scenario are as follows. So, so this is right. This is a straight line when t takes values in the real axis, and right, what may happen if the slope is rational, right? So then the trajectory closes. So this is rational slope. So the trajectory closes. And in this case, what is this subgroup G psi? What kind of subgroup of the torus do we get?
Circle.
Right. So this is isomorphic to S1. And of course, it may happen that the slope is irrational. And then, well, here I'm not sure I can draw an adequate picture, but we know that eventually it will be a dense subgroup. So, so what will it be as a subgroup? So here it was isomorphic to the circle, and here it will be isomorphic to what?
R.
Just to R, exactly. And its closure will be the torus T2. So that just to recall those simple things. Now, here is a fact. So the zero set of the vector field, of the fundamental vector field, which is generated, which corresponds to psi, is the same as the fixed point set of the corresponding one parameter subgroup. So this is probably to some extent more or less obvious. Do I need to make some comments about it? Probably not, right? So, and in particular, what is nice? So last time we discussed that the fixed point set of a subgroup coincides with a fixed point set of its closure. So the closure is a compact Lie group, and therefore this is a submanifold. So as a consequence, we see that in our case, when we look at the fundamental vector fields corresponding to the action of a compact Lie group, so those so sets of zeros, so they are submanifolds. Maybe just one small counterexample, just to show that this is not completely obvious. If you take a vector field which doesn't come from a group action, it's very easy to arrange it such that the set of zeros will not be a submanifold. Like, for instance, take Rm equal to R2 and take your vector field to be, for instance, xy d over dx, right? So then, of course, the set of zeros of V is a union of two straight lines which intersect at the origin, and this is not at all a submanifold, right? Because there would be this point at the origin which doesn't look like a point on a submanifold. So so this is an easy fact, but kind of from the perspective of vector fields is a non-trivial fact. So here this group action is somehow important. Right. Okay. One more notion that I would like to have about those actions of groups and Lie algebras. Let me perhaps start here. So now let me choose a point of M. Recall that to points we associated these stabilizer subgroups. Now what we can do, since we have those fundamental vector fields, we can introduce GM. And this is a set of xi's in G such that M is a zero of the corresponding vector field. Perhaps a small remark for those who know more about Lie groups and Lie algebras. So GM and G is Alekseev algebra. But okay, for a moment, we don't need to be concerned with that. So let me recall a little bit of geometry here. So we have a map from G, we said, to vector fields, and in fact, we induce those maps from the maps from G to tangent spaces, right? To each tangent space, we have a map from G. In fact, inside this TMM is sitting the tangent space to the orbit, right? And of course, the map here, it factors through the map to the orbit. And so the first remark is that this is surjective, right? Because the orbit is by definition what you get by the group action, and so this map has to be surjective. Now, here is sitting GM. This map is injective, right? And GM is exactly the kernel of that map, right? So the image of GM to G is, by definition of GM, is the kernel of G2 CM or M. One more remark about this notion. So GM is 0. Is the same as the capital GM, the stabilizer group is finite. So why is that? So that's because the maybe before doing that, maybe before doing that, let me make one small remark here and then come back to this statement. So this tells us the following. The dimension of the orbit through M is, of course, the dimension of its tangent space. And, well, this tells us, this sequence of maps tells us that this is exactly the difference of the dimension of G and the dimension of GM, right? Because, the dimension of the space is equal to the dimension of the kernel of the map plus dimension of the image. So this is the dimension of G. Minus the dimension of GM. I think what I'm saying here is nonsense, right? GM is equal to G. So now the formula helps me to get back on track, right? So GM equal to G. So this stabilizes Alekseev algebra equal to G if and only if GM. No, what I'm saying? No, what? What did I want to say? Right. Sorry, too early in the morning. Yeah, GM equal to 0 if and only if GM is finite, right? Right. So why is that? So that's because GM, we know it's a Lie subgroup. So it's a submanifold, compact submanifold of G of dimension equal to the dimension of GM. And this is 0. And a compact submanifold of a compact manifold of dimension 0, it has to be a finite set, right? Because otherwise it would have an accumulation point. Right. Okay. So I would torture you a little bit more with group actions. So up to now, we always had one manifold on which the group acted. Maybe just a brief discussion of a situation when you have two manifolds. So suppose we have a manifold M on which the group acts. We have a map, say some C infinity map to another manifold N, and here there is another group action. So the map is called equivariant if it commutes with the action. So we have F GM G F of M, of course for all G and G and all M in M. So that's the equivariance condition. Now we can play a little bit with those stabilizers. So what does it mean? So we're going to have a stabilizer for the first action, right? So these are G's and G such that GM equal to M. And well, now we're going to have an image under F of the point, and we're going to have a stabilizer. Let me call it N. Maybe the other way around. So N equal to F of M. And so these are What am I doing? So G acting on n is equal to n. Well, now a test question for you. There should be an inclusion between these groups. So what includes where? Yeah, I think that's yeah, so Gm includes in Gn. And that's because if G is in Gm, so we have G acting on f of m. So this is f of G acting on m. And this is f of m. So which means G is in Gn. Right. Right, so we have a group G. Inside of the group is sitting the stabilizer of the point in the target. And inside the stabilizer of the point in the target is sitting a stabilizer of the point in the source. Now maybe a couple of remarks about it. First of all, suppose we've now chosen a point in the target. So then, so there is a fiber of the target inside M. So the preimage of n in this source. By the way, like just a test question for you. What do you know about such sets? Are they submanifolds or are they nice? Are they not nice?
Derivative is not zero. It's a point is non-critical.
We'll probably we'll have to get back to this discussion. Maybe today, maybe next time. So the words regular value, they mean something? Okay. So they are, let's say, they're typically submanifolds, but sometimes not at all, right? So that's the kind of brief summary. Okay, but anyways, that's a subset of M. Now, what do you think? Does it carry a G action, this subset? Sorry? Sure, of course, depending on n, but not necessarily, right? But they always carry an action of Gn, right? So here we have an action of G. Inside G sitting Gn. And so this subset carries a Gn action. Right. Right. Okay. Maybe the last topic concerning the actions for a moment. So these are two important examples of actions. So the first one goes under the name of the adjoint action. And I think some of you probably know it very well. So that's the action of G on its Lie algebra. And it's organized in the following way. So recall that we have a conjugation action of G on itself. So G maps another element H to its conjugate. So in the beginning, when we started discussing group actions, we mentioned that there is always such a group action. And notice that here The stabilizer of the group unit is equal to the full group G. And this implies that the stabilizer acts on the tangent space at the group unit, right? And this is our Lie algebra. So this means that the Lie algebra comes equipped automatically with the action of the group. Now let me give you examples. So one set of examples, these are our favorite groups S1 and TK. So these groups are abelian. And this means that the conjugation action is trivial, right? So conjugation doesn't conjugate anything. Well, because of that, the adjoint action, yeah, so this is called, right, this is called the adjoint action. And there is a special notation for the corresponding operators at G. So at G is just identity. So that's, of course, a very, very simple and nice situation. And for like many, many cases, that will be just what we need. Let me give you just one more example. Recall that we were discussing the n-dimensional unitary group. So the complex matrices with Hermitian conjugate of G equal to G minus 1. And then we said that, so I think I gave you, right, the expression, what's the Lie algebra? These are what? So what's the Lie algebra? So let me write the answer probably again, and you tell me whether that's how you recall it. So these are anti-Hermitian matrices. I denote Hermitian matrices by Hn, and I multiply by imaginary unit. So these are, again, complex matrices such that A star is equal to minus A. Right? So now what's the adjoint action? So this turns out to be simply the action by conjugation. Maybe one small exercise. Check that indeed this, so it's clearly an action on complex matrices, but it's just a little bit less trivial to see that actually it preserves the set IHN, right? So this turns out to be the case, but maybe one needs to check it. Well, so the last thing. Coadjoint action. So adjoint action, I hope probably many of you heard about it. Coadjoint action, I don't know, maybe some of you heard about it, some of you maybe not. So that's the action of G on the dual of its Lie algebra. So it's defined in the following way. Once we have an action on the vector space, we automatically get an action on the dual. So that's a map, adjoint star from G to endomorphisms of G star. Which is defined by the following property. So we take an element of G dual, we take an element of G. So we want to figure out what is this thing. So this should be an element of G star. We need to evaluate it on all possible elements of G, and we simply declare that this is X adjoint G. And here, how is it? What would the experts say? I think it should be -1, right? If you want it to be an action. Right, so adjoint G -1. So that's the definition of adjoint G star. So is an action. Of course, for those who never checked it, maybe it's a good idea to check that indeed this formula defines an action. The same examples. In the abelian case, G equal to S1 and Tk, well, G, as we know, is Rk. Well, G star is also Rk. The adjoint action was trivial. Well, obviously the coadjoint action going to be trivial as well. And that's a very good news for us. So in many, many cases, so this coadjoint action does play an important role in the theory of moment maps, but in many, many cases it's just trivial, which is certainly very good news. Now, well, sometimes it's not trivial. What about this UN? Now, I will make a choice. So here, so this is, to some extent, the choice that I'm identifying the Lie algebra with anti-Hermitian matrices, but this choice is more or less canonical. Now I will make a choice which people typically make, but which is not quite canonical. So I would like to identify G star with the space of Hermitian matrices. So this is, I would say an isomorphism. This is actually a choice that I make, and I need to explain how Hn and IHn are in duality to each other. Right? So. And I choose the following funny duality. So let's say X psi. So this will be an element of Hn, and this will be an element of IHn. And I declare the pairing of X and psi to be the imaginary part of the trace X psi. You know, the imaginary part will kill this I. So this means this is more or less a pairing between Hermitian matrices with a trace, and then real part. So you can get rid of the imaginary part. So then there, of course, one needs to check that this is indeed a duality. But it turns out to be the case. So if this is a duality, then G star is identified with the space of Hermitian matrices. Now what's the coadjoint action? So what do you think it's going to be? So you have a unitary matrix. You're given a Hermitian matrix. We need to produce a new Hermitian matrix.
Gain conjugation.
Gain conjugation, yeah. So actually, that's the advantage of this choice. So it turns out that this exotic, right, coadjoint action becomes something that we know very well from linear algebra. That's the action of unitary matrices on Hermitian matrices by conjugation.
I'm just worried that in the definition of coadjoint, I translated G first there.
Yeah.
So
Let's write one line and see how it actually works. So let's start from the right-hand side. So the right-hand side now is imaginary of trace x, and here adjoint g minus 1. So this is g minus 1 psi g, right? Now watch my hands, right? That's the magic of traces. You have imaginary of trace, and I take this g and put it on the other side, right? So it is gx g minus 1 psi. And see exactly because of this g minus 1, that's why it's again a conjugation. So, sorry. All right, very well. So let me finish this hour with something that we already seen long time ago in the beginning of the course, the definition of a Hamiltonian G-space, and then we'll spend the next hour looking at simple properties of this definition. Well, so recall that the Hamiltonian G-space consists of a lot of data, and so one possibility is to package it into a triple. So in this triple, we have a G manifold M. We have omega, a 2 form on M. And we have a map mu from M to the dual of the Lie algebra. And here are several, I think also three properties. So the first property require M omega to be symplectic, meaning that omega is not degenerate and closed. So the second condition is that mu is equivariant. And what does it mean here? So of course, on M, we have our standard G action, and on G star, as we just discussed, that there is a God-given coadjoint action. So that's a somewhat, at the moment, probably it looks a little bit exotic for us because this coadjoint action is an exotic notion, but we'll get used to it. And finally, the third condition. we take a contraction of the, that's a complicated condition, so we have a contraction of omega with the fundamental vector field. And on the right-hand side, we get a differential of the pairing of the moment map with psi. And this is for all psi in G. So let me recall that, so this guy is a vector field on M. And maybe this guy also, maybe a small question what it is. So you see that's the map from M to vector space, right? So now we choose an element of the dual of this vector space. Dual of G star is G, so, and we pair the values with this psi. So this means that actually this combination is just a C infinity function on M. Right. So that's so that's maybe the one of the main definitions of the course. In the beginning, we had a definition of a symplectic manifold, now Hamiltonian G space. So we discussed, and maybe I should just repeat, this is a very, very successful definition, a little bit strange definition to start with, like many kind of this and this is still not so bad. This looks somewhat exotic, right? So we'll discuss the first simple properties of this definition after the break. So let me stay a little bit at this definition. I should probably say, so here I added many things. So this is really a strong definition. On some occasions, people consider weaker definitions. For instance, what you can do, you can say you have a symplectic structure and you have a G action, right? And you're not given a moment map at all. So 2 and 3 are absent. So then, for instance, you can ask, is there such a mu which satisfies 3? And even like kind of forget 2. So this is one possible question. And then you would have an existence and uniqueness question just for 3. And we'll come back to it and discuss it a little bit. And then assume that the answer, that the existence, the existence is okay. Then you can ask, but is there such a mu which on top of it satisfies 2? So in principle, you can kind of take it apart and kind of put it in different combinations. So here, this is more or less a maximal set of conditions that you may require. And to some extent, it's convenient for us to work with this maximal set of conditions, but in different situations, because you would often see in literature the discussion of existence and of uniqueness of moment maps and whether they are equivariant. And of course, from the point of view of this maximal definition, it sounds strange because for us it's just a part of definition, but you can actually set it up differently. One more thing. So I often call it a moment map, this mu, but there is the following terminology issue. So mu is a moment map, but many people call it a momentum map. So these are different schools of thought. So you can recognize the camp to which people belong by which word they're using. All right. I think like in American geography, moment map, this would be like the East Coast, and momentum map, the West Coast. Right. Okay, so let me start discussing some simple properties of those Hamiltonian G spaces and of, well, moment or momentum maps. So first of all, let me start with a technical remark. So mu is a map from M to G star. And so if we fix a point of the manifold, of course, mu induces a linear map between the corresponding tangent spaces. Now let me recall that so this space TMM together with the restriction of the two form is a symplectic vector space. Now what about this guy? So this is a tangent space to a vector space. So G star is a vector space. Therefore, it is, well, even not isomorphic, it is just equal to that vector space. So it's a copy. So this tangent space is a copy of G star. Now a proposition. So let's say GM omega mu is a Hamiltonian G space. And let's choose a point of the manifold. So then we can evaluate the kernel and the image of this map. So what's the kernel? So the kernel is the omega orthogonal to the tangent space of the orbit which passes through the point. And what's the image? So the image is the orthogonal of GM. So the Lie algebra stabilizer of the point M. And orthogonal, this means axis in G star such that so these are vectors in G star which vanish on GM. So it sounds technical, but now we need to start working with this definition, and that's one of the key features. So let's try. Let's try to see why it's true. So let me start with the following formula. I choose a vector in the tangent space. and I choose an element of G, and I would like to evaluate omega m on the following pair of vectors. So I take the value of the fundamental vector field at that point, and I take the vector v. Now, by condition 3 that I no longer have on the blackboard, but you have probably in your notes. So omega evaluated on the fundamental vector field, right? So that's the differential of the, so that's the differential of mu psi. So that's one form which is now evaluated on the vector field, v, on the vector v. So that's the value of this one form at m evaluated on v. And you see here there is a slight confusion with notations because so this pairing, that's the duality between the tangent space and the cotangent space. And this pairing is the duality between G and G star. I hope it's okay. We probably don't need more notation for that. Now, actually, so this is the same as mu m star of v psi. So this duality here, that's the duality between G and G star. So that was the duality between G and G star. And that's the duality of TMM. Right? Is it like, of course, this here, there is no problem in substance, but is there a problem with notation, or do you believe this is okay? Because right, what we have the differential of the map mu evaluated on v, but by definition that's mu m star of v, right? And it takes, because mu takes values in G star, that's why this guy takes values in G star. And then in the end, we want to pair it with psi. So actually, like, this means in the middle, I rewritten it in that way. Right, so I exchange the dualities. And then here, this is just a different notation for the same thing. Okay, so that's the first observation. Like, main difficulties with notation. Maybe I didn't optimize the notation. So now notice that if our vector is in the kernel of this map, this means that this right-hand side will be always 0, right, for all psi. So that's just the same. So that's just the same thing. Now, well, this means that's the same as omega m on this side. But now, these vectors, they span the tangent space to the orbit, right? We know that tangent space to the orbit is the image of this map of the Lie algebra into the tangent space. So what these equations say? These equations say that the pairing with omega of V with all the tangent vectors to the orbit is 0. But then by definition of omega orthogonal, this means that V is Tm omega orthogonal. Let's just test the definition of this omega orthogonal subspace. Right. So I think this settles the number one. So what about the number two? So let me first show that the image is contained in this GM orthogonal. So for that, let me do the following. Suppose that X is in the image of mu star M. So this means that X is equal to mu star M of V for some V in the tangent space. And this means that X psi is equal to, well, by the same equation, mu star M of V psi, and is equal to omega M psi M V. And this for all psi in G. Right, that's just the same equation once again. Now, if psi is in Gm, this means that the M is a 0 of psi M. And this means that the right-hand side vanishes. So X is orthogonal to Gm. So it vanishes on all the vectors from Gm. So now I proved that the image is sitting inside GM orthogonal. Now what remains to be seen why it is exactly equal to GM orthogonal. So that's the last. So that's the last step. And here we simply count the dimensions. So let's just count dimensions. So the dimension of this image, so what is it? Well, that's the dimension of the source minus the dimension of the kernel. Right? Now, what do we know about the kernel? The kernel, we know that this is the omega orthogonal to the tangent space to the orbit. So suppose we have a symplectic vector space, we have a subspace, and we have its omega orthogonal. What's the relation between the dimensions of the subspace and its omega orthogonal? Do you remember? So that's this. So the dimensions add up to the dimension of the space, right? So, which means that this is equal to the dimension of the orbit. Now, the dimension of the orbit that we discussed today, that's the dimension of G minus the dimension of Gm. Now you have a vector space, you have its subspace, and you have the orthogonal of the subspace in the dual. The dimension of the subspace and the dimension of the orthogonal in the dual add up to the dimension of the space, right? So actually this guy is equal to the dimension of Gm orthogonal. But now we have two subspaces, one of them inside the other. They have the same dimensions, so they are the same. So this was really an important statement. It's somewhat technical, but we're going to use it on many occasions. Let me, so I still today probably want to show you maybe just some remarks on the definition, and then also maybe one more proposition, but we'll see how it goes. So maybe still one remark on definition. Hamiltonian G spaces. So let's take this simplified assumption. So our group is a billion. It's a circle, or maybe it's a torus. So then, one nice thing, as we already discussed, so the coadjoint action is trivial. So this means that this second equivariance assumption for the moment map now becomes particularly nice. So it says m of g acting on m is mu of g acting on m is simply mu of m. So mu becomes a map from our manifold to a vector space to R or to Rk, and this map is simply G invariant. And it has a nice consequence. So let's say G is Tk and G is Rk. And let's choose two elements, Xi and eta, in Rk. So then functions mu Xi and mu eta are smooth functions on M, and they're actually, by this remark, G-invariant smooth functions. So recall we introduced those Poisson brackets associated to symplectic manifolds. So let's compute a Poisson bracket of these two functions. For that, let me recall how it's done. Right? So we should consider the Hamiltonian vector field corresponding to one of the functions and act with this vector field on the other one. So that's the definition. So one should take the Hamiltonian vector field of mu Xi and act on mu eta. Now the definition of the Hamiltonian vector field is as follows. Iota of V mu Xi omega should be equal to d mu Xi. So that's the definition of Hamiltonian vector field. But this definition, it is identical to our equation 3, where V mu Xi, we actually know what it is, right? So then, by 3, we know that V mu Xi is Xi m, the fundamental vector field which corresponds to the action. So this means that here we have Xi m acting on the function mu eta. Now, the function mu eta is invariant under the G action. We want to act on it by a fundamental vector field. What do we get? 0. Right. And this is by this G invariance. Yeah, so the different pieces, they cooperated and arranged on the blackboard in a nice way. So I think now everything fits. So what we proved? We proved that if the group is abelian, if it's a torus, for instance, then the Poisson brackets of all components of the moment map, they simply vanish. And so here there is a little bit of terminology that you can see in literature. So people would say that components of mu are in involution, whatever that means. So in fact, this simply means their Poisson brackets vanish. I'm not sure. It probably comes from some mechanics, but I don't quite know what involution they had in mind. But these are the terms which are used. Or we can say that mu, the map from R symplectic to G star isomorphic to RK is an integrable system. So these are the other words which mean exactly the same. So the Poisson brackets between components of this map, they all vanish. And this is an entry point to several big fields. We'll touch upon some of them in what follows in our course. Some of them we will never touch, but this is an important thing. Now I want to show you one more thing, one more property of moment maps today, if we have time. But first we need to recall one small thing that we already discussed a little bit. So we already mentioned regular values. And the setup is as follows. So you got a smooth map between two manifolds, or maybe whatever, some sufficiently differentiable map, or let's say smooth map, between two manifolds. And say if we fix a point of M, again, we have a map F star, which maps the tangent space to the source, to the tangent space of the target. And we say that the point of the target is a regular value of f if for all m in the preimage of n, this map F star of M is surjective. So what's good about regular values? Maybe let me first recall you a fact which is called Sartre's theorem. Which says that singular values, which is the complement of regular values, is null in the sense of Lebesgue measure. Right? So this singular set is very small. The set of regular values is huge. Now, how is it for those of you who know the story, also for those of you who don't know the story, doesn't it sound surprising? To me, it still sounds somewhat surprising because of the following. Suppose, and then kind of you explain me how it works. So suppose that so that's the map from the tangent space to M to the tangent space to N. Suppose that the dimension of M is smaller than the dimension of N. Right? So then this map simply has no chance to be surjective. It's kind of never surjective. Still, we claim that the regular values, so the huge majority of values is regular values. How does it go together?
Well, the image itself is going to be zero.
Absolutely, right. So the image is very small. And here the kind of course, it's a little bit of cheating. If this set is empty, then there is nothing to check, and we consider the value a regular value, right? So that one should have in mind, right? And if we don't check it, then, well, it's fine, right?
But we don't pose any conditions on F.
Sorry?
F is. But we don't pose any conditions
F
on
is,
F is just
yeah,
any.
whatever, differentiable, sufficiently differentiable. Let's say smooth, whatever. For the maps that we deal with, yeah, there are no conditions in F. So it's a kind of, so, but you know, it's one of the key statements in differential geometry. All various like kind of general positions, things, and like kind of infinite number of things in the basics of differential geometry. They are proved using this Sard's theorem. Now, another fact. Okay, so there is a lot of regular values, very well. Suppose that n is a regular value. So let me state it in some way and then kind of we discuss. Then the fiber, the level set, is a submanifold of dimension equal to the dimension of M minus the dimension of N. So here again, okay, depends a little bit. You can modify the statement. So here we assume that in case, you know, we fall in the situation when it's an empty set. Of course, an empty set is a manifold of any dimension, in particular a negative dimension if you want. Or you can say it's if non-empty. So this would avoid talking about those virtual so if non-empty. Of course, if it's empty, then well, there is not much to discuss. And that's maybe just to remind you. So this is not so difficult because once this derivative map is surjective, then there is a normal form. So this locally the map F is a projection, and the fibers of the projection locally they're just neighborhoods of origin in the vector space, and these are charts on our submanifold. Right. Now, one small proposition back to moment maps. So let's say GM omega mu Hamiltonian G space. And what do I want? And right. So then two things. First, X in G star is a regular value if and only if for all m in the fiber the stabilizers are finite. So all the points of the fiber have finite stabilizers. And second, so let's denote by I, or maybe by Ix. The embedding of the level set back to M. Recall, let's assume, assume that X in G star is a regular value. So then the fiber is a submanifold, and let's denote by Ix its embedding back to M. So then what we can do, we can restrict the two form to this submanifold. And we can look at its kernel. In principle, its restriction to the submanifold, to the tangent space to submanifold, doesn't need to be symplectic, right? It may have, as we discussed. So then it turns out that the kernel is exactly the tangent space at M of the orbit of M with respect to the action of the stabilizer of X under the coadjoint action. So recall the kind of, when you have this, those equivariant maps, then a stabilizer of a point here, it acts on the fiber back in this source manifold. So in there, it has an orbit, and this orbit passes through M, and it has a tangent space, right? So this tangent space is a subspace of the tangent space at M, and that's exactly the kernel. Does it still make sense? With difficulty. Right. I suggest the following. We prove the first statement, and the second statement, we start next time by like drawing all the pictures again and like kind of discussing what it means. But the first one is an easy one. So proof of one. I think this should be kind of more or less trivial, right? So X in G star is a regular value. By definition of a regular value, this means that for all points of the fiber, the differential is surjective, right? So this means that the image, right? The image of that map It's just the space G star. So this means that G star is equal to GM perp, because we computed the image and the image was GM perp. Now, if GM perp is the full space G star, this means GM is 0. So remember, that's the place where I had a confusion trying to wake up during the first hour. So, so GM is 0. And GM is 0, this means GM is finite. So you see, we now start already seeing kind of once we put together all this symplectic story together with a moment map. So it's kind of interesting that here we have, on the one hand, we have a symplectic structure, which is given by this 2 form, which equips all the tangent spaces with the symplectic structure. Then we have the G actions. So the G actions give you this rich structure. There are orbits, stabilizers, and all this nonsense we were discussing lately. And the moment maps. I think the moment maps, to some extent, they're our friends in this world. Because after all, moment maps are simply functions, right? Especially if you imagine, say, a group being S1, then the moment map is just one function. Or if it's a torus, it's just a set of k functions. So these are kind of, these are nice things. And now we start seeing there is a relation. Like, you see, being a regular value, this was a property of a function or a property of a map. And now somehow it's related to the property of the G action. So where the value, on the set of regular values, the G action is very, very, in some sense, simple, right? It has only finite stabilizers. It's not allowed to have like huge stabilizers. See, it's kind of already like we were suffering through those group actions, and we were a little bit suffering through those whatever, all those tangent maps. But now, well, that's a nice geometric, kind of interesting geometric statement. So, and kind of hopefully in what follows, kind of more interesting statements are to come and less suffering. So that's our slogan. Okay, well, that's it for today.